Hi Math 215 students. In this video, which deals with section 1.5 of our text, and in the next, we'll be talking about what are called homogeneous linear systems. The outcomes for this video are as follows, as shown here. There are a couple terms you want to add to your vocabulary. You want to be able to describe how to determine whether a homogeneous equation has a non-trivial solution, and to decide this for a given system of equations, or matrix vector equation. And so let's dive right in. The definition is as shown here. A homogeneous system of linear equations is one where the constant term in each equation equals 0. So we have an example on the left here. It's a system of linear equations like we've been dealing with so far. And you'll notice that in every one of these equations, what it is set equal to is 0. Every equation has equals 0 on the right-hand side. Now on the right, we also see an example of what we call a homogeneous matrix equation. A matrix equation is homogeneous if when you have AX equals B, the thing on the right-hand side is actually the 0 vector. So having zeros in all of the entries, this matrix vector equation actually corresponds to this system, as you can see, and we call each of these homogeneous for pretty much the same reason. It's because the right-hand side is equal to 0. Now, why are homogeneous systems worth defining and looking at? One reason is that homogeneous systems, or homogeneous matrix equations, are always consistent. There is always at least one solution to a homogeneous system of equations. And can you see why? Now, to give you a hint, we might take a look at the matrix vector equation, AX equals 0, which is a homogeneous matrix vector equation. If we were to forget for a second that A was a matrix, and just pretend that X was a regular variable, a scalar, 0 is just the number 0 instead of a 0 vector, then think about how you would solve this equation. If this were, for instance, 8x equals 0 rather than a, 8x equals 0 has what as its solution? Well, it's simply the solution x equals 0. You can think about dividing both sides by 8, but the point is that letting x equal 0, x itself be equal to 0, gives you a solution back in your introductory algebraic setting. Now here in the matrix vector setting, it also works. If you multiply the matrix A by the 0 vector, you're going to get the 0 vector out, so the 0 vector itself should be a solution. Now over in the systems of equations, what that would correspond to is letting each of the variables equal 0. And you can see that if I let x1 be 0, x2 be 0, and x3 be 0, that first equation is true. So the homogeneous equation always has a solution. The second equation is true, the third equation is true, by that solution of letting every variable equal 0. All right, so there is always at least one solution, namely the solution x equals 0. And you might not be impressed so much by that. That seems like a rather easy answer to the question of, is there a solution? And you might not be alone. This is called by mathematicians a trivial solution. So it's trivial in the sense that it's very easy, it's very simple to see why it's true. It's a trivial solution. Now, homogeneous systems of equations can have other solutions. They always have at least one solution, the 0 vector, but they could have more than one solution, right? Remember, a system of equations has 0, 1, or infinitely many solutions. So if there's more than one solution, we would call those solutions non-trivial solutions, solutions that are not equal to the 0 vector. So, for example, our first system of equations was a homogeneous system. We know that the 0 solution is always a solution. We could just let x1, x2, x3 equal 0. But if we were to solve this as we have solved systems in the past, we might set up the augmented matrix and then row reduce. And putting this matrix in reduced echelon form, we get something that looks like this. Now, as you translate that back into equations, we know that x1 should equal 2.5 times x3, x2 should equal 0, and x3 is a free variable. So if I go to write my solution, x2, x1, x2, x3, I know that x1 was equal to 2.5 times x3, x2 was equal to 0, and x3 was equal to x3. I can factor the x3 out and just write that the solution set is the set of all multiples, scalar multiples of the vector 2.501. So there are infinitely many solutions. The 0 vector is a solution. If we let x3 equal 0, we'll get the 0 vector out. But we could let x3 be anything else. And when we do, not all of the entries will be 0. In fact, we'll get infinitely many non-trivial solutions. All right, let's do one more example before moving on to the next video. In this example, we're asked, does the following homogeneous system have a non-trivial solution? And if so, what does the solution set look like? Now, this may strike you as a little bit odd because instead of having multiple equations in our system, we actually just have one, but it's a linear equation. We can talk about its solution set if we set it equal to 0. Now, we do know, of course, that this is homogeneous, so there's always at least one solution. You could always just let x1, x2, and x3 equal 0, but we're asked whether there are non-trivial solutions. So is there more than just the trivial solution? Are there multiple solutions? Well, to answer that question, we might think about what this would look like in an augmented matrix form, 1, negative 4, 7, 0. And if we were to look at this, this is already in reduced echelon form because we do have a 1 in that first spot there. So that 1 is actually our only pivot position, and so we can write x1 in terms of x2 and x3. This would say x1 minus 4x2 plus 7x3 is equal to 0, so rearranging that we would say that x1 is equal to 4x2 minus 7x3. x2 is a free variable in this system, x3 is a free variable in this system, so I can write my vector like that. But let me do a trick that will be helpful for the future. We'll come back and talk more about this in the next video, but I'm going to take this vector, which has a bunch of x2s and x3s, and I'm going to separate it into two vectors, the vector that contains the x2 parts of my entries, and the vector that contains the x3 parts of my entries. And once I do that, I'm going to factor x2 and x3 out so that it looks like x2 times 410 plus x3 times negative 701. Now, this is describing my solution set. So the solutions to this system of equations are actually anything you can get by scaling copies of 410 and negative 701 and adding them together. Now, of course, that is the description of a linear combination. So we're looking at all possible linear combinations of these two vectors, and the set of all possible linear combinations is exactly the span. So the solution set to this system of equations is the span of these two vectors. Now, geometrically, what that looks like, if you remember, the span of two vectors that are not multiples of each other is a plane, and so our solution set has the geometric form of a plane through R3. And if you remember back in your calculus or algebra classes, you might remember that if you have an equation involving x, y, and z set equal to a constant, it's actually the equation of some plane. Okay, now here are our outcomes again. Hopefully you can define these terms and you can describe how to tell whether there is a solution. I'll give you a hint, there is always a solution, but to find a non-trivial solution, what we have to do is solve our system of equations as before and just see if there's more than one solution. With that, we'll end this video, and we'll see you in the next one.